All right, this is part 3 of the Math 136 final review, looking at the start of the Day 2 material. So number 19 is express f of x equals negative 3x squared minus 6x minus 5 into the form a parentheses x minus h squared plus k, and then graph. So we're looking at putting a standard form quadratic into what we call vertex form. There are two ways to do this. The one that we went over in class, which had to do with learning it by a method that we had used before, which was how to do it by completing the square. So I'm going to do it that way first, and then I'm going to show you a quick way to check yourself if you are looking for just validation that you're doing that correctly. So to complete the square with something like this in function notation, we would first put all of the x terms in a group together, and then we leave a space for kind of a trinomial to be created. We leave the constant because it doesn't have an x after the blank, and we have a countering blank right after that. To complete the square, we need to have a 1 in front of our x squared, so we're going to pull out that negative 3 out of the x term parts, so that would be negative 3. That would leave me with x squared. Negative 6 divided by negative 3 would be positive 2x. We don't even know what's in the blank, so it's still going to be a blank. And then we would have our minus 5 and our counter blank. We take half of the middle term and then square it to complete the square here. So that would be 1 squared, which is 1. And that's what you add into this blank right here. Now, you have to be careful because you didn't really add just 1. You added something times 1. So this is negative 3 times 1. So we actually added negative 3 times 1, which is negative 3. To counter a negative 3, we need to add 3 out here. So whatever you put in this counter blank has to actually counter the distributive property right there. So then this would be f of x equals negative 3. This will factor into x plus 1 squared, because times 1 times 1, and then 1 plus 1 equals 2. And then minus 5, and positive 3 is negative 2. So that is my vertex form. A quick way to check yourself is to actually use the vertex formula to find the vertex to make sure it is the right numbers we see here. The vertex formula is negative b over 2a for the x, so that would have been negative negative 6 over 2 times negative 3, and that would be positive 6 over negative 6, which is negative 1. Now remember, when you plug something into this formula, you write x minus negative 1, so that's why we get a plus 1 here, so that makes sense. To find the ending number, you just have to plug negative 1 back into the function. So remember, this was another way of finding the vertex. So you don't have to do this if you're comfortable with completing the square, but if you're not comfortable with completing the square, this is another way to find h and k. And then when we plug that in, you get that's negative 1 squared is 1 times 3 is negative 3. Negative 6 times negative 1 is positive 6. And then we have our minus 5, and that makes negative 2. So notice our vertex is negative 1, negative 2. That's our vertex, which we could read just right off of here. It's always opposite of the inside of this and exactly this. So if you wanted to do this method to find your vertex, you could then just plug it in for h and k, and all you have to know is that a is the leading coefficient. So I could have just as easily gotten this formula just using my vertex formula, plugging it back in, and then knowing that a is always the leading coefficient. So then when we plot this, because that's really the gist here, we need to plot our vertex, so negative 1 down 2. I always put a V on that to distinguish that it's the vertex. And then I usually find one other point, and I try to keep my life simple. As long as the vertex is not on the y-axis, I plug in 0. If it's on the y-axis, I plug in 1 or negative 1. But if you plug in 0 for everything, you get negative 5. So there's a second point on this graph, 0, negative 5. So 0 and then down 1, 2, 3, 4, 5. And because this is a parabola, there is an axis of symmetry, remember, that goes kind of through here. So that means wherever there's a point on the right of the vertex, there's a matching point on the left. So then that gives me enough shape to draw my parabola, and it's going down. So that is number 19. For number 20, we have some parts that we're going to have to do. So we're doing f minus g of x, f divided by g of x, and then f of g of x. So we're going to be doing composition, division, and subtraction. And I'm going to move this down so I have enough room for all of these. So let's start off with subtraction. So we have f and we have g, and we're going to subtract the two functions from each other. So f of x minus g of x. We'll need to get a common denominator because we're trying to subtract. So I'm going to multiply this first fraction by x plus 5 on both top and bottom. I'm going to multiply the second fraction by the x minus 4. On top, I'll get 2x squared plus 10x. Be careful when you do the second one. This negative goes with the x when you distribute. So that would be negative x squared, and negative x times negative 4 would be positive 4x all over x minus 4, x plus 5. Combine like terms, we'll get x squared plus 14x over x minus 4, x plus 5. So that is the subtraction of those two functions. Part B has us doing the division. When you do the division, you stack the first fraction f over the second one. So, and that is important. You do want to stack first instead of jumping straight into multiplying by the reciprocal. And the reason for that is part D. They're going to have us go back and look at the domain of each of these. So you take the first fraction and you multiply by the reciprocal of the bottom fraction. So x plus 5 over x. Because x and 2x are both monomials, you can cross out the x's there because they're not binomials. So monomials can partially cancel like that, but not binomials. So then this would be a 2x plus 5 on top over an x minus 4. If you wanted to distribute out the 2 on top, you can, but it's fine to leave it as is. Okay, and then the last part before we do the domains is f of g. Remember, f of g means you write the f function and you plug the g function into it. So the f function was 2 blank over blank minus 4. All the blanks are where the x's used to be on f. Inside those blanks, we're going to plug g, which was x over x plus 5. Now to clean this up, we want to multiply everything on top and bottom by x plus 5. Notice that on the bottom, because there's a minus sign between these two parts, we will need to write it on both sides. On top, you just had one big term because there's no plus or minus connecting the 2 to this. So this would be x plus 5s are going to cancel, x plus 5s are going to cancel. My top is a 2x. My bottom, I still have the x that was on top, and then I need to distribute this negative 4. So negative 4x and minus 20. So I have 2x over negative 3x minus 20. And don't worry about the negative down there, that's fine. Okay, so let's talk about the domains real quick. The first one was very straightforward. If it's adding or subtracting, you just have to kind of look at the final result, and it looks like we need to throw out 4 and negative 5. So for f minus g of x, we need to throw out, the domain is that x cannot be 4 or negative 5. For f divided by g, you have to be a little bit more careful. So I'm going to go back up to that fraction. This is why we stack it. Anything in the denominator is going to be bad because it divides by 0, but this x is also in a denominator. It's in the big denominator. So even though that's a numerator, it's in a denominator of the other part of this fraction, which is the big fraction bar all the way across. So x can't equal 4, 0, or negative 5. So we have to throw in that element of 0. That's why it's important to stack that first. So x cannot equal, let's just keep them in the order 4, 0, negative 5. Composition, you have two things to consider. You have to look at the domain of the inside function and the domain of the final answer. The inside function was this red one, so definitely for the composition we can't have a -5. And that has to do with this red function we plugged in had a undefined value at -5. For the ending, you set the -3x minus 20 equal to 0 and divide that over. It looks like it's -20 over 3. So we also can't equal -20 over 3. So those are my different domains for this. All right, so let's move on to number 21. Excuse me. Okay, we're going to be graphing a polynomial. And the polynomial that we're graphing is got 4 terms. So to clean that up a little bit, let's try to factor by grouping. Also, I know that I'm going to be looking for some intervals at the end because I see this, when is the function bigger than 0 and when is the function less than 0. That reminds me of above the x-axis or below the x-axis. And we're going to eventually sketch the graph. So if I try to factor this, I can pull an x squared out of the first pair and a -4 out of the second pair. That would be a match, so that comes to the front. I also still have the leftovers of x squared minus 4, and that factors into another x plus 2 and x minus 2. So for x-intercepts, you set each of those equal to 0, so I get -2, 0 because of the x plus 2's, and 2, 0. So I could go ahead and put those dots, remember, on my graph at -2 and 2. To figure out if we're above or below on each side of those, we make a chart. So from -infinity to -2, from -2 to 2, and from 2 to infinity. You need to list your factors as many times as they show up. So I'm going to have an x plus 2, another x plus 2, and an x minus 2. I also need a test value for each region. And all we care about at the end is whether or not we get pluses or minuses, because that'll tell us how to graph it. So my test value is going to be less than -2 would be -3, between -2 and 2 would be 0, and bigger than 2 would be +3. So then remember, I plug those in. -3 plus 2 is negative, -3 plus 2 is negative, -3 minus 2 is negative. 3 negatives multiplied together is a negative. 0 plus 2 is positive, 0 plus 2 is positive, 0 minus 2 is negative. 1 negative is a negative. 3 plus 2 is positive, 3 plus 2 is positive, 3 minus 2 is positive. 3 positives multiply to make a positive. So notice I'm below, below, above. Because I had below back to back, that means there was a bounce on this graph. So these two are going to be below, and this one is going to be above. So when we're graphing, you start on the left side of the farthest point to the left. Since that's a B, we're going to go down. Between -2 and 2, we're supposed to also be below. So we go down some unknown amount and start coming back up. On the right side of +2, we're supposed to go above. So we keep going up. So notice I had a bounce at -2. That's because I had 2 x plus 2's pop up, and then I crossed straight through at +2. For this part right here, you're just telling me which of those intervals did which. So the only one that was greater than 0 was 2 to infinity. The ones that were less than 0 were these two, which we will separate with a union. So -infinity to -2 and -2 to 2. All right, let's look at 22. So 22 was, let's find the quotient and the remainder of this problem. So because this is x to the first power, I can use synthetic division. If it was higher than that, I would have to do long division. You can still use long division for this, but I'm actually going to use synthetic just because I find that it's easier not to deal with the x's. If you're going to use synthetic, remember that you need to solve this over first. If you're using long division, you leave it as x plus 2. So I'm going to have a negative 2, and then I start writing my numbers. Remember, I'm missing x to the 4th, x to the 3rd, and x here, so I'm going to need some placeholders. Our placeholder is always a 0. So I have a 3 for the x to the 5th, a 0 for the x to the 4th, a 0 for the x to the 3rd, a positive 6 for the x squared, a 0 for the x to the 1st, and then a 7. I pull down my first number in the column after this box, so that would be 3, and then we start multiplying. Negative 3 times 2, negative 2 times 3 is negative 6. Add the column. Negative 2 times negative 6 is positive 12. Add the column. Negative 2 times 12 is negative 24. Add the column. Negative 2 times negative 18 is positive 36. Add the column. Negative 2 times 36 is negative 72. And if we add that column, let's just do that one by calculator, make sure I'm right. That is negative 65. Okay, so your quotient is all of this information, your remainder's in the box. So we already know our R is negative 65. Our quotient is going to be 1 power less than what we started with, so that'll be x to the 4th. So 3x to the 4th minus 6x cubed plus 12x squared minus 18x plus 36. Notice I just grabbed each coefficient as I went along. Okay, for number 23, we're listing the potential rational zeros for the following equation. This is your P's over your Q's or C's over your D's, depending on which book you're more familiar with. We called it C's over D's in the 136 class. So this would be my C's, and this would be my D's, or P's over Q's if you were using the Sullivan textbook. So my factors of my C are plus or minus 1, plus or minus 2, so I'm doing factors of 36. Plus or minus 3 goes into it, plus or minus 4, plus or minus 6. 4 was times 9, so plus or minus 9. 3 was times 12. 2 was times 18, and 1 was times 36. Factors of 4 are plus or minus 1, plus or minus 2, plus or minus 4. So then we're supposed to stack every C over every D. So if you do all of them over 1, we know we're going to get plus or minus 1. And if you want to save some time, I will give you a little leniency because this is a long list. If you put a plus or minus and then a parentheses and then start your list with commas, I know that the plus or minus applies to everything. So 1, 2, 3, 4, 6, 9, 12, 18, and 36. All of those happen when you plug these over 1. If I put them over 2, we only list it if it's a new number. So 1 over 2 is a half. 2 over 2 is 1, which we already had. 3 over 2 is new, since it doesn't divide evenly. 4 over 2 would be 2, which we already have in our list. 6 over 2 is 3, we already have that. 9 over 2 is new. 12 over 2 is 6, which we already had in our list. 18 over 2 is 9, which we already have. And 36 over 2 is 18, so we already have that in the list. So now we need to do everything over 4. So 1 over 4 is new. 2 over 4 is a half, which we already have. 3 over 4 is new. 4 over 4 is 1, which we already have. 6 over 4 is 3 over 2, which we already have. 9 over 4 is new. 12 over 4 is 3, which we have. 18 over 4 reduces down to 9 halves, which we already have. And 36 over 4 is 9, which we already have. So that would be my complete list with no repeats. Now notice, this was just listing. We're not supposed to find any zeros. So all we had to do was come up with this list. Whereas on number 24, not only do we have to find the list of P's over Q's or C's over D's, we actually have to find the zeros, the solutions. So let's look at this one. I'm going to give myself plenty of room. For this one, we need to list our factors of the constant over our factors of the leading coefficient. So our C's are plus or minus 1, plus this is 50, plus or minus 2. 3 doesn't go evenly, 4 doesn't go evenly, 5 doesn't go, 5 does go evenly, 5 and 10, 2 and 25, and 1 and 50. I believe that is my full list. For factors of the leading coefficient, we're looking at 2, so that would just be plus or minus 1, plus or minus 2. So my list of C's over D's is plus or minus 1, 2, 5, 10, 25, and 50. And then I put them over 2, so that would be a half. 2 over 2 is 1. 5 over 2 is new. 10 over 2 is 5. 25 over 2 is new. And 50 over 2 is 25. So once you come up with your list, remember these are all positives and negatives, we start trying synthetic division. So I always just start out with positive 1. We place out all of our coefficients. No gaps. This went cubed, squared, x to the first and no x. So no zeros were needed. So we pull down the 2, we multiply, we add the column, we multiply, we add the column, we multiply, and we add the column. If this column equals 0, we've found a nice answer. If it doesn't, it's not any use to us. So 1 doesn't work. We try negative 1, that would be 2, negative 11, negative 5, and 50 again. Pull down the 2, that would be negative 2, that's negative 13. That would be positive 13, that would be 8, and that would be negative 8, which is 42. So it's not negative 1. Let's try positive 2. So 2, negative 11, negative 5, and 50 again. Pull down the 2, that would be 4. That would be negative 7. That would be negative 14. That would be negative 19. And that would be negative 38, which would be, I believe, it's going to be a positive 12 because I did subtraction backwards. So again, not helping us. Let's try negative 2. I'm just going to go through my list. So 2, negative 11, negative 5, and 50. So this would be 2. That would be negative 4. That would be negative 15. That would be 30. That would be 25, and that is negative 50. Yay, we found a 0. So what does that mean for us? Well, that means when we go to list our final blank on the answer key on the test, one of our zeros will be the answer, negative 2. We're not going to make you factor it, you just have to tell me the answers. This part right here will give us our other 2 solutions. Now that that was x cubed, this is going to be broken down now to x squared. And it'll be set equal to 0 because we're trying to solve it for the remaining 2 solutions. If this factors, then you will be able to get the solutions right away. If not, you'll have to use quadratic formula. I believe this does factor because if you do 2 times 25, that would be 50. And 2 factors of 50 that have the same sign and add to negative 15 would be negative 5 and negative 10. So I'm going to be able to solve this by factor by grouping. So this pair has an x in common, that would be 2x minus 5. This pair has a negative 5 in common, so that would be 2x minus 5. So my factors are 2x minus 5 and x minus 5. So I get x equals 5, and 2x minus 5 would be add 5 and divide by 2. So x equals 5 halves. So my 3 solutions total are negative 2, 5 halves, and 5. Okay, let's look at 25. This is a graphing problem where we are graphing a rational function. This is when we want to talk about asymptotes, holes, intercepts. So remember, we have our list of things we care about, our domain, our vertical asymptotes, our x-intercepts, whether or not we have holes, whether or not we have a y-intercept, a horizontal asymptote, or an oblique, because you have one or the other. So domain is found by factoring the bottom and making sure you know what would make it equal 0. So for us, x cannot equal 6. Since that factor is not going to cancel out, that means it is a vertical asymptote. So x equals 6. X-intercepts means you have to have x's on top. We have none, so we don't have any x-intercepts. Holes come if only something had canceled out as a factor. Nothing canceled. The y-intercept is found by plugging in 0 for all the x's. So 4 over negative 6 would be negative 2/3. So 0, negative 2/3. The horizontal versus oblique has to do with your powers of x's on top and bottom. If your power of x's is bigger on bottom than on top, that means you can't divide this by long division. That means you have a horizontal asymptote that goes 0 times. So that means we don't have an oblique. Okay, so let's put our vertical asymptote at positive 6. So 1, 2, 3, 4, 5, 6. I'm actually going to count by 2's, make myself have a little bit more of a scaled graph. So 2, 4, 6. Just so my graph wasn't right there at the edge. So I counted by 2's. On your graph on the test, you should have more room. For my horizontal asymptote, I'm at y equals 0. So y equals 0, x equals 6. Because remember, we counted by 2's, so 2, 4, 6. 0, negative 2/3 will be really close to this, somewhere in here. So my y-intercept's below the blue line. And that's all the information I have from there. So if I want to graph this, I need some more x's and y's. So I need to pick numbers to the left of the vertical asymptote and to the right. So I'm going to pick, let's say, 4 and 2, and let's say 8 and 10. So just stick with the evens to make it spaced out nice. So this would be 4 over 2 minus 6. That would be 4 over negative 4, so that's negative 1. This would be 4 over 4 minus 6, so that's 4 over negative 2, so that's negative 2. 4 over 8 minus 6 is 4 over positive 2, which is 2. And 4 over 10 minus 6 would be 4 over 4, which is 1. So 4 was at negative 2, which I counted by 1's on the y-axis. You can do that as long as you're consistent all the way across the axis and then consistent all the way down the y's. And then 4, negative 2, 2, negative 1. So that makes sense because that's kind of lined up with my y-intercept there. 8 is going to be right here up to positive 2, and 10 would be positive 1. Now, because of our vertical asymptote and our horizontal asymptote, that means this is stuck in this top region of blue and red, and all of this is stuck in this bottom region, following those asymptotes. So that's what my graph looks like. Remember, if you wanted to test whether or not you cross the horizontal asymptote, you would have to set the horizontal asymptote equal to the function and solve. But we're not going to give you one on the test that needs to cross the horizontal asymptote, so I wouldn't stress about that part. 26 is pretty much a similar graph, except this one has some stuff that factors in the bottom. So we have 2 domain restrictions. X can't equal negative 3 or 3. Neither one of them will cancel with the top factor, so that means they are both vertical asymptotes. The only time one of them can't be a vertical asymptote is if it cancels out. X-intercepts. I do have an x on top. If you set 3x squared equal to 0, x is going to have to equal 0. So we are going to cross the x-axis at 0, 0. We don't have any holes because nothing canceled out when we factored. The y-intercept, since the x-intercept is 0, 0, this is also 0, 0, but remember you can find the y-intercept by plugging in 0 for all your x's, which is 0 over negative 9, which is 0. Oblique, and horizontal asymptote. Which one do I have? Well, when you look at this, you could divide here. X squared would go into 3x squared 3 times, so that means we have a horizontal asymptote since it went in a number of times. The reason that is, another way you can know that is that the power on top and the power on bottom are exactly the same, so we use the coefficients in front of each of those leading parts, so 3 over 1. So we go up 1, 2, 3, that would be my horizontal asymptote. I have 2 vertical asymptotes of -3 and +3. I have an x-intercept of 0, 0, and that's also my y-intercept. And I'm going to need some more points. So when you do your table, when you pick stuff to plug in, you need to make sure you pick things that are going to be on each side of the vertical asymptotes and x-intercepts. So I'm going to have some separators here of -3, 0, and 3, because that's my x-intercept right there and my 2 vertical asymptotes. So I'm going to pick -4, -5, -2, -1, 1, 2, and 4, 5. Just pick values on each side of those numbers. To save time, I'm going to plug them in using my calculator. So 3 times -5 squared would be 3 times 25. Divided by, that would be 25 squared minus 9. Or sorry, 5 squared minus 9. So 25 minus 9. So this would be 4.7. If we plug in 4, that would be 3 times 4 squared is going to be 16. And it doesn't matter that it's negative because you're squaring it, so it's going to end up positive. So my top is 48. -4 squared is again 16, but 16 minus 9 is going to be 7. So that would be 6.9. -2, so 3 times -2 squared would be 3 times 4, divided by 4 minus 9. So that's -2.4. If we plug in -1, that would be 3 on top, divided by -8 on the bottom. So that's -0.38. And then you're going to get symmetry from this point, because when you plug in the same number but it's positive, you're squaring them, so they're all going to turn out the same. You can check that on your calculator, but it is going to be true. So let's plot these. -5 is at 4.7. -4 is at 6.9. So it looks like this is on this top half of the graph. -2 is at -2.4. -1 is at -0.38. So this looks like this is headed down towards this blue asymptote. Then the same thing on the other side. So this is also headed down. And then this is for 6.9 again, and 5, 4.7. So this is in this top region. All right, this is the last one for part 3 of the videos. And it is 27, find the inverse of this function. So remember, to find an inverse, think of this as the letter y, and we're going to swap all of our x's and y's. That's like swapping our domain and range. So this would now be x equals 3y minus 1 over y minus 2. To solve this for y now, we would need to cross multiply. So x times y, x times -2, so that'd be -2x. And then 1 times all of this would still be 3y minus 1. You want to regroup the y's, or solve for them. So we need to subtract over the 3y and add over the 2x, because the 2x does not have a y. We don't want it on the same side. The reason you want to get all the y's on the same side is you want to factor out the y. So then once you get that y factored out, you can divide the x minus 3 over. So then this would be my inverse, which we do want to write as f inverse of x. So that's the inverse. Now, for the domain and range, remember we have this little chart. Domain and range. The function originally x could not equal 2. For the ending inverse, x can't equal 3 because that would make that denominator 0. And the cool thing is the ranges, remember, are just the flip-flop of those domains. So x couldn't be 2 here, so y can't be 2 in the opposite function. X could not be 3 in the inverse, so y can't be 3 in the original. And that's it for the domain and range. All right, so this is the end of the part 3. I will be shortly posting the part 4 as well.